this is where things get weird. Okay, because if you are a dot, okay, and I create, so this is a floor, okay, and this is a, okay, you are a dot. Can you be here and here at the same time? Can you? You cannot. This is what happened in wave mechanics. What if I open a little door, tiny door? There's a little hole, okay, a little hole. Now let's say, let me make it look bigger. So this is you. And I open just a little hole here. Can you get from here to there? You cannot. You cannot, because you are here, you can't get in there. It's too small a hole, right? But if you're not a hole, if you're not a dot, you're not a particle, so to speak. That's what the word I should have used. You are a distribution. There's actually a tiny distribution that leads over here. Okay? So actually, there is a tiny probability that you would actually be over here. So think of a quantum car. You come in the house, you go in, you close the garage door, but you leave just centimeters of gap in here, okay? Because your car is not an object, it's not a particle, it's not a dot, it's not a particle, it's a wave. And when you square that wave, you get probability. When you come in the next morning and you look at where the car is, okay? Now, the concept is this is a wave until you look at it. Once you look at it, it becomes a dot again. That's called collapse. So actually, you can do this 100 times. But actually, you know, 99 of the times, you park the car inside, you come in the next morning, you look at where the car is, it is inside. But maybe one every 100 nights, you park the car in here, you close the garage door, but you leave a little bit room open. That leaks the probability. You wake up the next morning and your car is right here. That's called quantum tunneling. That's called quantum tunneling. Okay, that's called quantum tunneling. Okay, that's where things get weird. Are you? I'm going to say, do you believe this, or do you have any problem with this? Okay. If you have problem with this, all I can do is sympathize, because at a small scale, I'm talking about the size of atoms, beyond smaller than nanoscale, things start to get like this. In fact, at nanoscale, you already start having this kind of effect. Okay, it's quantum tunneling. Okay, this is where things get weird. Okay, now, why does this matter? Why does this matter? Well, I have to tell you that there are three things that gets weird. This, and this. Okay, three things. Okay, these two things help quantum. To make a long story short, this two things makes quantum computing possible. This thing makes classical computing not possible. Okay, let me say that again. There are three quantum effects. These two quantum effects, which is a property, I only talk about the first one, right? So I only talk about the first one. The three things get weird, three ways. One, quantum tunneling. Okay, quantum tunneling makes classical computing stop. Quantum superposition and quantum entanglement. These two makes quantum computing possible, or okay. So impossible. Okay. So quantum tunneling makes classical computing impossible. But wait a minute, you've been doing classical computing all this time. So obviously it is possible. It is when it gets small that this is impossible. So why is this a problem of your generation and not my generation? Anybody? Anybody? Because of this. This is called Moore's law, right? Moore's law is the sort of like doubling of computational power every so many years. Oops. Okay. The point is that computer gets more powerful because the individual binary gate, the 0 and 1, implemented on binary on computer semiconductor chips, gets smaller. The point is this: it used to be about 10 nanometer. Okay, we're talking about nanoscale, right? And it gets smaller. So sorry, let's start with 10 micrometer. It gets to nanometer, nanometer, nanometer. Once it gets to today, okay, nowadays we get to about 7 nanometer. It's like saying that you used to have something like this. Okay, so let's say when a binary digit was this big, okay, when it was this big, now semiconductor doesn't close the door completely. What it does is it does a bit like this. So when it was about 10 micrometer, you can say this is closed, right? And you can say that this is open. You can say this is open. Oops, how do you erase that? Okay, you can say that. So you can say that this is closed. Okay, because at this size, at about 10 micron, 800 nanometer, 90 nanometer, 10 nanometer, it can't get through. Okay, it could, but the probability is so minuscule, it basically doesn't happen. Okay, but once you get to this size, like 7 nanometer, then it gets so small that the wave description, it's like it's kind of weird. The bigger you are, the more precise the wave function is. So let me put it this way: if you are precise, okay, if the particle is big, it's the same thing as saying that the distribution looks like this. Okay, and so when you have a door like this, it can't get through. But when the particle is small, it's like saying this is a distribution. Okay, and it starts to leak into here. That's what happened. This is called limit of Moore's law. So quantum computing is relevant to you not because you are greedy, you want something better than classical computing. Yeah, it is part of your greed because your greed is to make things smaller and smaller and more powerful. The point is that up to a point, you can't. Up to a point, when you get so small, quantum tunneling happens. And what does quantum tunneling look like? It looks like this. Okay? The energy, instead of, so if you think of a particle moving as a wave, instead of bouncing back, it leaks some probability. So this is a probability that's leaked. You can see that there's some light over here. It's not completely dark. See, it's a tiny, so this is what I mean. Okay, this is the same picture, much better drawn, by the way. Okay, so when you get to that level, semiconductor doesn't work anymore, or it would not work if you get smaller than this. So Quantum computing, okay, it's not about this. It's a quantum effect that stopped Moore's law going. But quantum computing is not about this. This is like a problem and opportunity. But quantum computing is the opportunity, okay? So this thing has nothing to do with quantum computing. It just simply say that you can't keep going forever with classical computing. You can't make it smaller and smaller and more powerful, okay? Now the story of quantum beginning starts, okay? Quantum superposition, okay? Now this is probably the most conceptually important thing. A classical bit, okay? A classical bit has to be 1 or 0. Okay, a classical bit has to be 1 or 0. It can either be here or here, here or here, here or here. It cannot be both. If it gets to both, it breaks down. It breaks down. Okay? Quantum bit, on the other hand, is always kind of both. Well, not always, most of the time. And the way to think about it is, you know, if you can't beat them, join them. If you can't stop the probability to be on either side, so this is 0, okay? This is 0. And this is 1. Okay? So binary digit works this way, right? It's either 0 or 1. 0 or 1. Quantum bit is a little bit of both. So it has certain probability of 0 and certain probability of 1. So in this case, if I instead of drawing probability like a curve, right? I draw it as a stick, right? So it's a wave function. Once you square the wave function to get the probability, but instead of getting this shape probability, you get this shape, a stick. Now, a quantum bit, okay? If you think of classical bit, it's like all the way here and 0, or 0 and all the way here. Quantum bit means, yeah, it's about 70% here and 30% here. That's what it means. But instead of breaking down, we embrace this. Okay, let me say that again. So this is the best story you will ever tell, say, your children, whenever you want to say, you know, obstacle or problem turns into opportunity. This is the moment. The problem with classical computing is when you get small enough, probability leaks. So you don't have a definite 0 or 1. If you don't have definite 0 or 1, computational paradigm breaks down, becomes error. That's the problem. The opportunity is to say, well, with quantum computing, we say, what if we start with something that is neither 0 nor 1, but a little bit of both? What can we do with it? Okay, so think about it, right? Think about it. This is really, you know, back to my slides here about science, right? What if you have phenomena which is 0 or 1 in a definite sense? Semiconducting property is 0 or 1 in a definite sense. What can you do with it? You can build a digital computer. Now, the discovery is you have something that breaks this down. Okay. Okay. So this is a story of classical computer. A classical quantum computer story would be something like quantum tunneling. Okay. So this is what makes classical computing possible. This is what makes classical computing impossible. Should we make the chips smaller? Okay, so it's not impossible yet, it's going to be impossible. So in that sense, classical quantum computing embraces but it's not the quantum tunneling that it embraces. It's this next thing I'm talking about. Okay, so superposition is exactly why quantum tunneling happens, but think of it as opportunity. Okay, now, so go back to here. This is all I want you to see. Stare at this and oops, sorry. Until it makes sense to you. Okay, instead of 0 or 1, it is A times 0 plus B times 1. This is a mathematical notation for the wave function. The probability of being 0 is equal to A squared. Okay, so remember I told you that the wave function has to be square. So this is it. This is this guy. Okay, this is this guy, this wave function. Okay, Schrodinger's wave function applies to anything small. Now I'm going to apply to what's called qubit, quantum binary digit. That quantum binary digit doesn't have a sort of like a bell shape. It has a 2 shape to it. It is A times being 0 plus B times being 1. This is called quantum state. Oops, why did I? Yeah. Okay, this is a quantum state. Okay, now when you open the box, you look at it, you have to get some answer. It's either it's either 1 or 0. Just like when you come in the next day, you turn on the light, the car is either in the garage or outside the garage with some probability. Okay, but it's no longer kind of both. Okay, so that's what we mean by quantum collapse. Okay, so quantum collapse is when you have something that's quantum collapse turns wave function into definite position like classical mechanics. Okay, quantum collapse. So qubit, so an ordinary bit is always either 0 or 1, but quantum bit so let's call this classical bit now, because okay, when in is a superposition of 0 and 1, and that superposition is described by A, and this is a funny notation, but get used to it. It's called bracket notation. Okay. Turns into quantum bit turns into classical bit value 0 with probability A squared is equal to probability that quantum bit turns into class. Okay, let's do that. Okay. So obviously, A squared plus B squared equals to 1. Okay, that's it. Okay, so instead of crying that the bit falls apart, quantum computer scientists ask, what can you do with qubit? Okay, so you turn obstacle into opportunity, and that's where we come in. Now there is okay, this is, by the way, something you can probably watch for fun. This is the superposition. Okay, it's like saying, if you have a quantum bit, right? If bit is 0, you don't turn on the switch. If bit is 1, you turn on the switch. The switch breaks the glass of poison gas and kills the cat. So this is called Schrodinger's cat. Okay, so you have either 1 or 0. If it's, you know, before that it's 0 and 1. So a cat is both alive and dead. Right? It's not saying that it's already alive, dead. You don't know it. That's like tossing a coin, collapse it in your hand, and then not looking at it. Right? If you spin a coin, head or tail, head or tail, head or tail, and you clap your hand, but you don't open it, it's already head or tail. You just don't know it. But Schrodinger's cat is different. It's saying that the coin is still spinning. So the cat is still both dead and alive with, in this case, equal probability because it's 1/2. Okay, and that's the paradox. Okay, that's the paradox. The point is that once you open the lid to examine if the cat is alive or dead, it's like turning on the light and see if the car is in the garage or outside. That moment, the quantum uncertainty becomes classical certainty. You get either 0, the cat's alive, or 1, the machine starts working, breaks the glass, the poison comes out, and the cat's dead. Okay. And this is a joke that the USB is also in a quantum state because, you know, you never know. That's a joke. Okay. Quantum entanglement. Well, this is something more powerful, but it's a little bit more advanced. It's saying that whereas classical bits, right, can be independently set to 0 and 1. You can move, you have a strings, right? You have a string. So with a classical bit, we have something like 1 0 0 1. Okay, you can independently do this. You can turn this. Now, with quantum bit, you can, first of all, you don't have a definite, you have a combination. But let's say once you turn it to a classical bit, you can also make sure that you end up with something like this. But entanglement means you can also hook up the bits together so that they somehow coordinate and say something like, if 1 turns 0, I'm going to all turn to 0. Or something like, if 1 turns to 1, everybody goes to 1. It's some kind of like, a synchronization of nature. This is called entanglement. Okay, this is entanglement. That's what gave it the teleportation capability, but we're not going to talk about it. Anyway, entanglement is something that Einstein did not like. You know why? Anybody knows why? Because if I entangle 2 bits, right, one of them is either 1 or 0, the other one is either 1 or 0. You don't know which one is going to be. But because of this quantum magic called entanglement, they don't all have to be entangled. But once you entangle them, they have this kind of cosmic connection where if you take 1 bit to one end of the universe, you take another bit to another end of the universe, you still don't know if it's going to be 1 or 0. But at one end of the universe, if you collapse your hand, you open up and you see it's a 1, you can be 100% sure that at the other end of the universe, the other bit is also 1. Simultaneously, immediately. So that's faster than speed of light because it's instantaneous, right? It takes you 10 minutes from light to go from here to the sun. But you can be across the universe, right? 92 million light years, right? And you have one entangled bit over here and the other entangled bit. Once you know it's 1, the other one is 1. Once you know it's 0, the other one is always 0. This is something that Einstein cannot accept. It's called spooky action at a distance. Okay. Now, many of you are probably smart enough to think of something called hidden variable theory. Okay, well, obviously, the reason that they have the same value is because they've had the same value all along. They just don't tell you about it. Well, that turns out to be impossible, and that's proven by what's called Bell inequality. I'm not going to go into that, but let's just say that nature is that weird. It's not that you spin two coins, but they are entangled coins. You take one coin to one edge of the universe, you take the other coin to the other edge of the universe, and they know, the coins know it's going to be head. No, it doesn't. It literally does not know until that moment. But for some reason, if one end of the universe you get a head, the other end of the universe, that coin will also be a head. If you get a tail, the other end of the universe, the other coin will immediately also becomes a tail. Okay, not like it's spinning, and when you collapse, it is collapsed at that moment. Okay, it's instantaneous. Okay, it's very cosmic thing. Okay, so that, by the way, is what makes teleportation and all that. But we'll talk about teleportation later. Okay. Anyway, so let's get to more practical thing. Okay, let's get to more practical thing. Now, this is where you have to pay a very close attention. Okay, I'm going back in history a little bit. I'm saying, hey, what about classical computing? Okay, what if you embrace binary digit? What kind of computing can you do? In other words, it's like you have a genie. Okay, a genie grants you some wish, but that genie can only grant you one magic. That magic is ability to manipulate strings of zeros and one. Okay, and you were born in 1850. Okay, in 1850, there's no such thing as a digital computer. There's a mechanical calculator by Charles Babbage. But okay, in the 1850, you were visited by an angel or a genie. A genie grants you this superhuman power to manipulate zeros and one. How do you manipulate 0 and 1? You can only manipulate it through binary logic. Okay? You can only use this binary logic. Now, what's binary logic? You can do something like not A. Well, first of all, A becomes A. Okay, do nothing. A becomes not A. Okay. By the way, A can only be 0 and 1. Okay. Not A. Okay. So let's call it B for Boolean. 0 and 1 is called Boolean from mathematician named Boolean. Okay. So you can do this. You can do something like B and B2. Okay, you can do something like B or B2. Okay, for example, if B is male and B1 is male or not male or female, B2 is adult or child, B and B2 means you are adult, male or not. All right? Okay, so what about OR? Well, OR is bigger set because you can actually be adult and male. You can be adult but not male, or you can be male and not adult. That's called OR. Okay, and there is this thing called B1 XOR B2. XOR is like if B, you can be male or adult but not both. Okay, so this is like a screening process, right? You come in. I'm going to take a vaccine screening. Okay, if you adult, okay, so back then when the vaccine was kind of scarce, they used this rule: you are adult and diabetic, you get a vaccine. Okay, if you're not both adult and diabetic, you don't get a vaccine. Okay, when you get more vaccine available, you get something like this. If you are adult, you get a vaccine. If you are diabetic, even if you're not adult, you get a vaccine. Or if you're both, you get a vaccine. Okay, but you can have something like this, where for some reason, if you're both adult and diabetic, it makes your body so weak you can't take the vaccine. So it's XOR. It has to be one thing that's true. Either B1 is true or B2 is true, but not both. Okay, XOR is very important. Okay, so XOR is very important. Why? Because it does this. You guys know how to do this, right? Binary number. Basically, this is, imagine, again, a genie came and granted you the power of binary manipulation. Then you are making a computer that adds. You used to have abacus. You want to create a new adding machine. You know that you can add this number, right? In binary, this number is 0, 0, 0. This is 0 plus 1 equal to 1. This 0 plus 1 equal to 2. But notice the right handmost digit that I'm making really big is the same thing as XOR. 0, 0 becomes 0. 0 and 1 becomes 1. Or also 1 and 0 becomes 1. Okay? Oops. Okay, I can do this as well. 1 and 0. 1 and 0. Okay? So 1 plus 0 becomes.
I was wondering, what if like in zeros there are a little bit of 1 and in 1 there's a little bit of 0?
That's where you get the quantum bit. Now don't go to quantum bit yet. You can't. Again, this is classical, right? Classical.
Oh, okay.
Okay, this is classical computing. Okay, so you can't. And in fact, to be honest with you, quantum computer is a terrible adding machine. Okay, so quantum computing is, it can crack your bank account, but it can't add two numbers very well. It can, but it's completely inefficient. Okay, simply because of that. Okay, so if you're gonna add two numbers together, like 0 and 0 plus equal to 0, 1 plus 0, or 0 plus 1 equal to 1, don't use quantum computer, guys. Okay, don't use quantum computer. Okay, so this is what happened. Okay, so if you focus just on the right hand side, it's actually doing this. So you're sitting there, you're saying, hey, wait a minute, a genie just granted me a power of doing manipulation, XOR, gave you this function. What can you do? You turn to mathematics and you say that adding in binary form is equivalent with respect to the right hand digit to XOR. So you make this leap mathematically, right? Right? You make this leap mathematically, okay? Right? The science hasn't happened yet because back then you don't even know about things that can be 0 and 1 like in a small scale. You don't have a semiconductor. You're sitting in 18th century. You just have this math, okay? Now, but if, let's say, you happen to have a friend, okay, let's say it's not 1850, but 1900. You don't have transistor, but you have vacuum tube. Vacuum tube can also turn on 0 and 1. So now you have vacuum tube. So, okay, it's terrible, but at least it's worked. You put this together, you can literally engineer an adding machine. So you can make an adding machine out of vacuum tube because you have this principle of XOR, right? XOR. You have the science and engineering of vacuum tube, and then you can make an adding machine. Okay, you can invent that, and you can invent adding machine. So that's it. So computer is some kind of physical machine that implements computational logic. In fact, if you look at it that way, forget about the fact that you have silicon chip. You can have analog computers. You can have computers that's made of vacuum tubes. You can make computers that makes of individual transistor. In fact, you know, in the old days, you can shoot rockets with transistor. You could choose rocket with calculate trajectory of rocket with vacuum tube as well. Okay, so you have this. You have abacus, you know, in the Chinese history, electromechanical computer, vacuum tube, transistor. It's only now that you have this. This happens after the World War II. Okay, and so broaden your understanding of computing. Computing is like being granted some power of manipulation and turn that into some kind of useful calculation. And even though you can add 1 and 2, you know that if you can do this in principle, the difference between a machine and a human being is human beings do not scale. That's the difference, right? You can add 1 and 1, 1 and 0, 0 and 1, 0 and 0 much faster than a computer. But if you have billions of digits, you lose out to computer. So the inventor know this. They know that, you know, for adding 0 and 1, you know, it's a long way. It'sขี่ช้างจับตั๊กแตน, right? It's a terrible way of adding 0 and 1. But you know that you can scale it. That's the crux of it. You can scale this technology, whereas human being, you cannot scale. Okay, so armed with that knowledge, they create the whole thing called computer, very fundamental computer circuitry, right? How do you add number? How do you, basically you have this. How do you turn 1 into 1, 0 into 0, or turn 1 into 0, 0 into 1? How do you do this? How do you do this? How do you do this? And then you build a whole bunch of things. You turn multiplication into addition of logarithm, whatever. Okay, you have all kinds of tricks. And then you build up from there. Now, you are going to do the same thing, but you build up from thing that is neither 1 nor 0, but a little bit of both. Okay, and that's where, okay. So this again is a slide that describes classical computing. By the way, this is a slide that I spent a lot of time on this, and I want you to really look at it. See? This is actually the electrical circuitry that implements this thing here. Okay, so this is semiconductor. Depending on, I don't know if you can see, there's a current coming in and there's a current going out. But whether or not it comes in and comes out depends on this third one. So this is kind of like coming in, runs into a door, and this is a door opener. This is what a transistor does. And you have gazillion of them in your iPhone. Well, millions, billions, millions, billions of them in your iPhone. You have a bunch of these. Okay? And each of them does basic things like adding and negating and so forth, and you build that up. So it implements this. Okay, and it's called, this is, by the way, it's called half adder. Okay, so you keep doing this, keep doing this, keep doing this, keep doing this. So why is classical information, what's a classical information processing? Information is stored in bit. Now you have to remember these two sentences until the day you die, I guess. What's classical information processing? I'm going to ask this on exam. Information is stored in bits. Processing is performed by logic gates or sequence of logic gates on store bits. That's it. Okay. It turns out that this plus implementation of this on silicon chips is what drives the whole world today. It's information processing in this paradigm on this thing, except this thing is so tiny, you can pack 1 billion of them in a microchip the size of your thumb. Okay. Now this is the exciting part. Instead of turning failure into failure, you turn it into success. You say, wait a minute, it's so sad that when you get so small, you can't control it anymore. You can't make it 0 or 1. It's always a combination of both. Yeah, it turns into 0 or 1, But before that, it's in the mixture. Hey, let's exploit that. Let's exploit that. So if you think of it this way, okay, if you think of it this way, okay, again, you with your wife, right? Or your husband, and your child has gone off, right? And so you say you look right, you look first floor, then look to the right. Okay, that's it, right? So, i.e., so I'm going to denote this as 0, 1. Okay, 0 and 1. I'm going to say, look on the first floor, and then look to the left. Okay, and that's called 0, 0. Okay, that's just my notation. And then I have 2 more. Look on the other floor. Let's say there's only 2 floors, right? And to the right is equal to 1, 1. And this one is equal to 1, 0. Okay, now in order to make sure that you look everywhere, how many steps? And this is where, you know, you parallelize, right? It'd be nice if you have 2 of you, okay? You over here, first floor, your wife go to the second floor, but she still has to look right and left. So let's say there are 4 of you, okay? You, your wife, and 2 older brother, 1 older sister, okay? So you and the older brother go on the first floor, you go to the right, the brother go on the left. Your wife and the sister go to the second floor. And this is terrible because you're making ladies walk. So maybe I should switch the example around. Okay, your wife and your daughter goes on the second floor. Your wife goes to the right and your child goes to the left. So you have 2 choices. If there's 1 person, you have 4 steps. If you have 4 person, you have 1 step. Okay, so you have this trade-off between, so you have a trade-off. Okay, 1 person looking times 4 steps versus 2 person, well, let's make it 4 person looking 1 step per person. Okay. Okay. This, the latter is called, parallel search. Okay. So that is the power of parallelism. Okay. Now I ask you, what if you can do one person in 1 step? Wouldn't that be nice? Okay. And this is where you go to the spiritual world, and this is where you sort of like do some kind of magic. You divide your soul into 4 and send them separately. Okay, that'd be nice, right? So it's 1 person, 1 step. But in order to do that, you have to divide your soul into 4 parts. Okay, well, in this case, with qubit, let's say n qubit, okay, with n qubit, you with 1 qubit, let's say 1 qubit can divide into 2 souls. 2 qubits can divide into 4 souls. n qubit can divide into how many? How many would say 2n? Let me say 2n. It's not. It's 2 to the power n. So, and that's the essence of why quantum computing is a game changer. Okay? It can do this. It can do this. Now, between 2n and n to the power of 2, well, that looks kind of innocuously very similar. But let me show you this number. This is the number. Okay? This is when n is equal to 50. This is what? This is 8. This is 6 million. So that makes it 5 trillion. So this is 1,000 trillion, 1 mega trillion. Okay? So can you imagine, right? Can you imagine if you have ordinary computers, you have say 50 bits, 50 bits. You have to alternatively switch yes, no, yes, no, yes, no. You have to do this, okay, in sequence, right? So 1, 2, 3, 4. So how many sequences do you have? How many combination can you look? You can look this many combination, but you have to look at it one at a time. One at a time. You look at this, then this, right? Because you have one computer, or you can have mega trillion computers. Okay, that's not possible either. But anyway, let's say you have one classical computer. One classical computer, if it takes a microsecond to do this, it's still longer than the age of the universe. Okay, because it's setting one thing at a time. So it's doing this. Check this, check this, check this, check this. Okay, a quantum computer, okay, with 50 qubits can divide its soul into q to the n and just do this computation maybe in one step. Maybe not in one step, but certainly not in mega trillion step. Okay, maybe in 10 steps. Okay? Maybe there's some pre-processing you need to do and blah blah. But at the end of the day, you're not doing mega trillion steps. That is why we want to do quantum computing. That is why computer security is threatened. Because to make a long story short, and when we go to the blockchain class, we'll talk about cryptography and I can teach you why. But ultimately, okay, you finding some number in some combination of number. And a classical computer can only search one at a time. You have to search half of this in order to have a 50-50 probability of finding, okay? Because quantum computing, a 50-bit quantum computing can divide its soul into this many parts. It can find all the solution almost simultaneously, not quite, okay? But in number of steps, finite, very tiny number of steps. Okay. This is why quantum computing is the disruptive technology that disrupts everything else, because everything else is still digital silicon quantum classical computer driven. Okay, so if blockchain disrupt banking, quantum computing would disrupt blockchain. That's what they mean. That's what, okay, so let's write that. By virtue of, and then this is in detail, okay? But that's a trick. That's a trick. That's a trick. Again, what's the trick? Well, just like when I told you that it has to collapse, right? You can't separate your soul forever. You can separate your soul and search for your missing child. And at some point you have to collapse. All the divided soul has to come back and report. Ah, your child is on the second floor to the left of the department store. Just like that, I have to search, once I separate the quantum soul into 2 to the n part, I search over this combination, I have to come back and collapse to a single value. Okay, that single value would be a 50 ordinary bit. So it could be 101111101111. Okay, so that's the solution. By the way, this is a very fun site. It's called Numbermatics. So quantum computing is the quantum mechanical binary digit. That's what it does. Okay, I'm going to skip some of this, and if we have time, I'll go over this video. This video is a very good video. It's a bit long, and this guy not only is giving a very clear explanation, but his chart is one of those. Let me look at this chart there. So this chart here is very good, and I wouldn't waste time redrawing any of this. It's a beautiful chart. It's quite gorgeous. Anyway, it describes in principle how you would turn this into mathematical operation. So just like you have mathematical operation that turns 1 into 0, 0 into 1, you have this kind of mathematical operation on combination of 0 and 1. And that's where linear algebra comes into play. You guys see this? This looks like linear algebra, right? Yeah, it is linear algebra. Okay. So let me go to one slide that he has that I think starts, and this is good. This is good. The circular one. Okay. Now, never mind. Just ignore everything. Okay. All I'm saying is that when we talk about binary digit, you have 2 things. Either the first bit is 0 or the second bit is 0. Okay. So you can think of it as this: 0, 1 or 1, 0. It can also be 0, 0 and 1, 1, but it's not represented here. Okay. Well, binary, okay, quantum bit is not showing 0 and 1. This is the A and B, guys. This is the A and B. So if this is A is equal to 0, it has 0 probability of being 0. Okay, or something like that. Okay. Actually, I put the other way around. So this one has 100% probability of being 0, 0 probability of being 1. This one has 0 probability of being 0, 100% probability of being 1. So between here and here, those are the 2 states that a binary digit in your computer can do. Either this or that, this or that. Quantum bit can be any combination. In particular, in this program, it uses 1, 2, 3, 4, 5, 6 more combination. In this case, A is equal to 1 divided by square root 2, and B is equal to 1 square root 2. So this one has 1 square root 2 square, so that's 1/2 probability of 1, and 1/2 probability of being 0. So this is kind of equal, 50-50, right? So this is all 0, this is all 1, this is 50-50. Okay? And so not only can it be 50-50, it can be something else. Okay? But in this example, he restricts it to be 50-50, all 0, all 1. Okay? The interesting here is all the manipulation is equivalent to moving down, up and down. Now, all these are different, right? But if you square them, it's the same. If you square this, you get 1/2, 1/2. If you square this, you get 1/2, 1/2, 1/2, 1/2. So all this internal state represent 50-50 probability of head, 50-50 probability of tail. This one and this one has the same probability. This one and this one has the same probability. Okay. So anyway, gorgeous slides. I mean, I can't do any better. This is wonderful. Okay. And so manipulation of bits is the arrow. It's just basically moving this thing. Okay, so you start with some information. Let's say you start with information. You encode it here. You manipulate it, you move it around. You end up with here, say. And then you take the probability and you get the result. Now, if you end up here, you get inconclusive result. If you end up here, you get definite result. Okay, so here's definite, 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 definite. This is 50, 50, 50, 50. And that's why quantum computing requires you to do this many times so you can run the probability. Okay, so that's it. That's it. Okay, so that's like encoding, looking for lost child or looking for the prime number factoring that's going to hack your bank account. By encoding in here, moving it around, blah, 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 get the result, and then decoding. That's what it means. Okay. This is a gorgeous slide. Okay. But okay. So this is more detail. And I actually, if you look in detail, there's a minute marker for all these slides, right? So you can see that all this explanation. Again, I'm using this slide. This is an exam. This is a mathematical example. I show you about a heart search. Okay, this is looking for your child basically. Okay. Now, this is actually a screenshot of my quantum program. So literally, I programmed this using this kind of thing. This is, you know, remember I told you that fundamentally it's about XOR and operation. Well, computer code doesn't look like XOR code or OR. But ultimately, when you go down at the very basic level, it's logic gate. Well, with quantum computing, we're now at the stage where we're actually manipulating the logic gate directly. So if I send in this code, this is our logic gate. Okay, it's gonna make a computation. The right answer, okay, this is a wrong answer, wrong answer, wrong answer, right answer. See that? What quantum computing does is it ran this thing maybe 1,000 times or 1,000,000 times. And sometimes it gets the wrong answer. Sometimes it gets the wrong answer. So think of A and B. Instead of A, B, we have A, B, C, D, right? And this is A squared, this is B squared, this is C squared, this is D squared. So this has a high probability, and that's your solution. So you don't get exact result, right? The quantum computing is about encoding your problem into qubits, doing some kind of operation like I program here. I just copy the example, right? Run this 1,000 times with the assurance that the right answer will occur with the highest probability. So once you get this plot, if you ran it 2 times, maybe you get this and this. But if you ran it 1,000,000 times, you will get something like this. And I'm pretty sure the answer is this. And it is the correct answer because I wrote the thing, so I know what the right answer is. The right answer is this. So the quantum is going to give you the right answer with highest probability. It's not going to give you one answer, by the way, unless you have something very trivial. Okay, but the point is that by the time you get to this, you're pretty sure this is the right answer. Okay. Teleportation, and I'm not going to talk about this. Use this thing which is entanglement, but anyway. So this is it. This is what I mean by quantum computing is a disruptive technology because it can crack this. You can crack this number. Okay. Try to find 2 numbers that are primes and multiply and get this. The combination is even bigger than this number. I told you this number that looks pretty big, right? Well, the combination that will give you that you have to search to find this product is even bigger than that. Okay, but have no fear. Once quantum crack classical cryptography, what do? You do quantum cryptography. So that's another story. So don't worry that your bank account is going to get hacked by a quantum computer, because just as you have quantum algorithm for hacking classical encryption, you also have quantum encryption. So Anyway, so these are all very, very, this is sort of like a, tail end of the talk and give you the idea. Now I'll give you one last thing, and I think this is going to be something that's going to give you a power, an understanding of the power. Okay, and this is called, I'm kind of like doing this. So right now, can you guys see what I'm getting to, right? Okay, so at the end of the day, quantum computing encode your search hard into the machine. Okay, run quantum computing algorithm, and then read the result corresponding to the highest probability. And that's your answer. Answer is equal to quantum collapse result corresponding to the highest probability. Okay, so obviously you run this a few times. That's it. Okay, and this is the power. Now, let me show you how this works. Okay, I'm not going to show you the Shor algorithm. That's very difficult. Okay, even I can't replicate it from here, but I can show you this one, Grover. Video into and paste that. Problem. Find a needle. Okay. Now, in order for classical computer to do this, classical computer has 1/2 50% chance of finding this in 2 to the power n divided by 2 step. Okay. Now, I'm just going to give you the result. Quantum computing has whatever percentage chance, X% chance of finding this in I don't have the number exactly, but something, but in the order of square root n. Yeah. In other words, yeah, if you look at this number, yeah, there. Okay, let's say that I have a needle, okay, and my haystack has this many hay, mega trillion, we call it room if you want, okay? We have mega trillion boxes, and I'm hiding a diamond in one box. Okay, so this is the number of possible hiding place. Okay, and so for classical computer to get a 50-50 chance of finding one, you cannot do anything. There's nothing guiding you, right? So you just search one by one. Once you get to half of that, or 500 trillion boxes, you have a 50% chance of getting one. Okay, so multiply that by the number of microseconds it takes to check. Trust me, it's going to be huge. It's going to be longer than the age of the universe. But if I have an algorithm, and let's say each step, instead of taking microseconds, let's say take an hour. One step takes an hour. Okay, what's the worst that can happen? Well, you can say something like, you take the square root of 50, which is about 7, right? Because 50 is about 49. So square root of 50 is about 7. The number of steps, let's say, is about an hour to do this proportionally. So what's the worst can happen? Maybe 2 times that. So 2 hours. That's 14 hours. 14 hours is still shorter than the age of the universe. So it's not even comparable. It makes something that's not doable under the age of the universe. It do something that, you know, maybe last a few hours or weeks. Doesn't matter, okay? So if you think of cracking the bank code, on the one side, it takes classical computer, the age of universe, to crack RSA 256 or something, say, okay, a banking encryption. But if you have a quantum computer of 50 qubits, you can crack this in, say, 7 hours. That's what it means. That's what it means. Now, I'll tell you a story. I'll tell you not to be so optimistic or pessimistic, however you see it. The point is that, remember I told you that quantum binary is like spinning coins, right? And then they collapse. The point is that that coin is so sensitive. As you're spinning, if you sneeze, that coin will collapse. Let me say that again. Quantum bit is like a coin that is so sensitive that while it's either 0 or 1, if you sneeze hard enough, it will collapse. And that's the reason why you have this machine. You know what this machine is? It looks like all this connection, right? It's making like a wire. No, actually, all this connection is refrigeration. I think, I'm pretty sure that is. Okay? The real quantum computer is probably somewhere here. Okay? All this as apparatus is there to cool it. Why? Because heat is like shaking that chopstick that I was telling you about. It's like sneezing. It's giving shaking. If you shake the system ever so slightly, the quantum collapse. In other words, before it gets to do all this manipulation, it immediately stops. It becomes 1 or 0. It doesn't go on. Okay, it's kind of trying to move this, blah blah blah. But before it gets any far to complete the algorithm, it collapses, becomes 0 and 1, wrongly. Okay, so you can't sneeze around quantum computer. Sneezing is a form of shaking. Shaking is like heat. Okay, so to minimize sneezing around the quantum computer is like cooling the environment. So all the quantum computing engineering side is about making refrigerator. Okay, it's about making refrigerator.
Can we put the quantum computer outside of the refrigerator, but in like a cold place, like North Pole or something like that?
Oh, well, it turns out that this is colder than North Pole. Okay, North Pole is not cold enough. It's not cold enough. Okay, they're not doing this refrigerator because they don't feel like going to the North Pole and they want to do this in Philadelphia or something. It's not. That's not the point. The point is that even at North Pole, it's not cold enough. There's latent heat in the atmosphere. Okay, so if you think about, you know how cold North Pole is. How cold is North? That's not very cold. Okay. Now it's minus 40. So that's about equivalent to about 230 degrees Kelvin. Okay. Because a 0 Kelvin, a 0 Celsius is 273. So minus 40 degrees, right? So that's about 233 Kelvin. How cold does quantum computer need to be? Okay. I hate Fahrenheit. Come on. What's 450? Anybody quickly? 450. So wait a second. So it's 450. Sorry. Yeah, 450. Sorry, 460. 460. Okay. And then
128 Celsius.
Yeah. Okay. So 128 Celsius.
828.
No, it can't be. It can't be. It's a. You have to.
Wait.
Okay.
No. Actually, it's negative.
So you have to make it. Yeah, you minus 460, right? Right. But 0 is at 30, so you have to another 30 or 32. 492. 492, right? Right. And then you have to multiply by 5 divided by 9 minus 723. You know what that is? That is nearly 0. Nearly 0 Kelvin. Okay. So absolute kit. Okay. So look at this number. Look at this number. Minus 277.7. And what's absolute 0? Okay. So that number was actually approximate. You don't need to get, you can't get below this. So it's not minus 277.3. It's probably minus 277.0 or something like that. Okay. So actually, you have to get it, you know, you go to the North Pole and cool by further 230 degrees. So that's just not doable. Okay. So that's why you have to do it in a lab. Okay. Again, heat. What's heat? Heat is nothing more than molecule knocking each other about. What's molecule knocking? Well, that's like shaking, right? So I have this tiny thing that's spinning in a quantum scale. If I shake it at the molecular scale, it's going to stop everything, right? So that's it. That's the challenge. The challenge is not to create a quantum computer. Okay. In fact, if you shine any laser, you almost automatically create a quantum computer by definition. Well, not quite. But the problem is to create a quantum computer that stays cool enough to do a couple of these steps. Okay. Keep this thing running for about 7 hours. And that is very difficult. Okay. And it gets more difficult because, you know, to keep 1 qubit cool, it's hard. To keep 5 qubit cool is hard. That's why the machine that I ran this experiment on only had 5 qubits. Okay, 5 qubits. And you need something like, to crack RSA encryption, you need about maybe 40 qubits or something. I don't know. Okay, they do some kind of mathematical estimation. So the way to get around it is to have what's called redundancy. Okay, it's called error correction. So what it means is that to get a good 50 qubits, you may need to produce 500 qubits spare. So that's even tougher. So in terms of hardware, it's hard. It's not there yet. Okay, but you know, think about it. You used to have 1 transistor, and now you have gazillion transistors, millions of transistors in your iPhone. Okay, so scaling from 2 to 1 million is a technological barrier that you have seen overcome in your lifetime. Okay. So again, you know, the technology that you require is basically refrigeration. All the algorithm, let me show you this. And this is can go back to these slides. Okay. Long before you have this internet banking, this algorithm can already crack internet banking. This algorithm in 1994. And that was before internet banking was a thing, right? And so somewhere down the line, we have internet banking and we have internet everything. And all of this can be cracked by this. But what is not happening is the refrigerator that can keep 50 qubits whole enough to do its thing for about 7 hours, let's say. Okay. So don't panic yet. Don't panic. Okay. So that's the story. But anyway, I might cover this in later, but I can certainly tell you right now what's with this guy. So this Grover algorithm, okay, what it does this, okay, it does this. It makes all quantum state equally likely. It makes equally likely. That's like here, okay, equally likely. All this, okay. So if you think about it, if I have let's say instead of 2 to the n hiding place, let's say I have 2 to the 3 hiding place. Okay, so I have 8 places. So I have 1 8 1 8 1 8 1 8. Okay, so I have basically 8 number, right? Instead of have A, B, C, D, E, F, G, H number. Okay, so this is A times 0 0 0 plus B times 0 0 1 plus C times 0 0 1 0. You get the picture, right? Okay. So let's say A equal to B equal to C equal H. So probability of anything is equal to what? It's equal to 1/8. Okay. Now, what does that look like? Let's go to here. And this is a magic, and this looks almost like magic. It is magic. Okay, so you have this thing. Okay, now this is what Grover algorithm does. It splits the soul, and it say if you found the key, say the key is hidden here. If you found the key, you flip your value. Okay, you flip your value. So let's say, for example, let's say the diamond is hidden in room 010. Okay. What happened is that you say A is equal to A, B is equal to B, and then C is equal to minus C. Okay, and then everybody else the same. Okay, and so on. So let's see what that picture looks like. So this is gonna be like this, except you will have so on. Okay, now what the algorithm does is, again, all this bits are entangled. So it's kind of like together. So that's why I call it separating the soul. It's the same soul. So I take the average of this. Take the average, okay? And then I flip the value around the average. What happened when I flip this value? It gets lower, right? So let's make a new value. So this value flips, so I get this thing. Gets smaller. This thing gets smaller. This thing gets smaller. This thing gets smaller. This thing gets smaller. How about this guy? When I flip around here, it actually gets bigger. So after one iteration, instead of having A, B, C, D, E, F, G, the new one looks like this. Right? So once again, I flip this, I take the average, I flip it around the average. Next time, this thing is going to be even higher. Okay? Then perform a flip around the resulting average. This result in amplitude amplification. Okay, in other words, makes absolute value of C, hence C square, hence probability of higher. Okay, do this 3 times and you almost guarantee that you will get the picture like this. Okay. Now, in this case, I only have 4 places to hide. Okay. This is even simpler, right? So you only need to do, square root of 2, like 2 iterations. Okay. 2 iteration, but you do this a million times, right? Because each time is a 2 iteration. Each time is a 2 iteration. Now, if so this number can be huge, right? Once again, this is only 4, but this algorithm can do this. Okay. So that's called. Now, for those of you who are not, if you appreciate what's happening here, you would actually probably get a goosebump to be able to find, okay, in square root of 50 steps, things that are hidden in 2 to the 50 hiding places. That is it's just mind-boggling. I mean, you should get a goosebump right now, as I nearly do. And that's what quantum computing is. Okay, so it's a very difficult concept, but again, this is to go back to wrap up this lecture again, right? Instead of this, now, so I have one story for this. Now, with binary, I don't think of binary logical gate like this. I have something like Hadamard gate, basically quantum qubit gate. Okay, so it's not going to have a name like XOR. It's going to have funny names. Okay, so let's go to internet and say, give me an example of quantum gate. You get funny names. Quantum logic gates. You get Hadamard. But these are not funny names. They're name of the authors. Okay, Pauli, named after physicist named Pauli. Pauli X, Pauli Y, Pauli Z. Phase, Hadamard. So instead of having a control none. So you have different kind of mathematics. So here, one version, you have binary logical operator. Here, you have this thing instead. Okay. Quantum logic gate. Okay, here I might as well put it in the right name, which is Boolean logic. Binary and Boolean usually right? And then you have, things like poly, X, Y, Z. So those are 3, by the way. And then Hadamard, this is very important. And so 8 of them. Okay. So this thing, all these gates are doing what? It's doing this. It's doing this. Okay. And this is 1 bit, quantum bit. This is 1 quantum bit. If you have 50 of them, okay. Okay, you just line them up and you do a few things, but you entangle. The problem, the essence is that even though you line them up here, you can do some kind of operation that entangles them. And this is a bit that is very difficult to explain. It's not independent. And this is why you have this kind of, spiritual coordination between your search path. This is the reason why you can do this, right? Take the average of everyone and then flip it around because they're not operating independently. Okay, you line up regular classical bit, and unless you give them individual instructions that are coordinated, they're just going to do their own thing. But in this case, when you put quantum things together, you can somehow magically tie them up together and coordinate their action and their computation. And it's very hard to give you the definition. Okay, so that entanglement is what's possible. Okay, because if you had just superposition, then certainly you can do, maybe you can do this, right? Everybody has the same probability, but you can't, what can you do from there? You have to be able to manipulate one and all, not one or the other, all of them. And that's where entanglement comes in. And that's I may not be saying things technically correct, but I'm trying to give the intuition. Okay, so you have to, you encode search problem into superposition of states, and then you rely on quantum entanglement, quantum effect, in particular, using this thing called quantum algorithm to do that, to tell the computer to do things. Okay, and these steps here, let me just show you, just to make sure. Yeah, this step here, this bit, by the way, this is the entanglement. And you will see that I used it here as well. I think here. Hadamard, yeah. This is to initialize it to make all the bits equally likely, and this is kind of to entangle them, blah, blah, blah. And I think this is polygates. I don't remember now. Okay. But anyway, it did this. This is not simulation. They have software that does simulation, but IBM promised us that if you send the instruction to them, they'll put in the queue, and maybe when the computer, when this thing is not doing anything, it will execute the code for you. So apparently, I was able to do in 2018, able to, run instruction in one of these guys at temperature near 0. Okay. So that's quite amazing. So anyway, so that's okay. So we kind of run out of time, and next week we'll have the exam. All right.